This glowing, lopsided donut is the first radio image of Sagittarius A star, the supermassive black hole at the center of our Milky Way galaxy. What looks like a flat ring of hot gas is an elaborate optical illusion engineered by extreme gravity. Immense gravitational mass actively manipulates and warps any light passing near the horizon, long before that light is ever trapped. We can deconstruct this image by looking at how gravity stretches light in two distinct ways, physically bending its path through space and draining the energy from its waves. Decoding these gravitational tricks is the only way we can measure and observe an object that is otherwise completely invisible. Mass dictates the shape of the universe. A highly concentrated mass creates a steep, deep well in the fabric of spacetime, severely distorting the environment. Light naturally travels in a straight line, but approaching this gravity well, it's forced to follow a curved trajectory called a geodesic. Because this curvature is so severe, light emitted from behind the black hole gets pulled over the poles, redirecting toward our telescopes. The intense bending of light from the far side of the accretion disk creates a distinct, bright circle of light known as the photon ring. This ring shape maps the black hole's gravity, warping the fabric of space, tracing a geometry that exists far beyond the gas itself. If we look closely at that image of Sagittarius A star, another anomaly stands out. The ring is significantly brighter on one side than the other. The gas in this accretion disk is orbiting the center at a significant fraction of the speed of light. At relativistic speeds, Doppler beaming drastically alters how we perceive the energy of these light waves. As superheated gas races toward us, its light waves bunch together, shifting to the blue spectrum and appearing intensely bright. On the opposite side, gas rotating away stretches those waves apart. They shift toward the red spectrum, losing energy and fading in brightness. That stark contrast between the compressed, bright waves and the stretched, dim waves creates the illusion of a lopsided, uneven ring. This brightness asymmetry acts as a visual speedometer, proving the extreme rotational velocity of the matter swirling around the event horizon. Now imagine a luminous, glowing object caught in an endless freefall, sinking slowly toward the darkness of a perfectly spherical void. General relativity dictates a strange paradox for an outside observer. From a safe distance, that object never appears to cross the event horizon. It simply freezes. As the object falls deeper into the gravity well, its emitted light must expend massive amounts of energy just to climb back out to our eyes. Light cannot travel slower than the speed of light, so to shed energy, the physical distance between its wave peaks elongates, a process called gravitational redshift. The light is stretched from visible colors down into infrared, and eventually into long radio waves. As those wavelengths stretch, the rate of photons reaching the observer's eyes slows to a trickle. The frozen, falling object gradually dims to absolutely nothing. The black hole effectively erases infalling matter, stretching its light so severely that it simply fades out of the visible universe. This radio image of Sagittarius A star serves as a high-fidelity map of warped spacetime. The bright ring proves light paths are being bent into circles, and the dark, fading interior proves wavelengths are being stretched to infinity. Black holes hide their interiors by stretching escaping light until time and information dissipate into the dark, leaving us staring at the absolute